All right, let's do this. Oh, Clement, now we're recording. Thanks so much for coming on my show.
Well, thanks for having me.
Your name came up in in my earlier episode with Phil, and then we got to talking, and now I think you'd be a really good guest. So let's see. So you are a mathematician.
Absolutely.
And we overlapped while you were a postdoc and I was a grad student at Columbia.
That's right.
And now you are in Switzerland.
That's right. So we overlapped in between 2010 and 2014. That's when I was in New York. Yeah, I've been in Switzerland, well, almost ever before 2010 and definitely after 2014. So I'm Swiss. Yeah, from there.
Math. Let's talk about some math. So, I mean,
Sure.
I know the math that you used to do had to do with statistical mechanics, conformal field theory, complex analysis. Is that how you would describe it?
That's yes, except that it's still math. It's math that I still do now.
Okay. So
but absolutely. Yeah. I mean, I started, a journey that kind of led me to conformal field theory. I mean, this journey didn't start, with me even knowing what conformal field theory was about. It started in probability. So I always liked graphs and random objects. So it naturally led me to study, probability related to graphs. And, at some point, when I was still
like what,
an undergrad,
like Ramsey theory or something?
Sorry?
Like Ramsey theory or Ramanujan?
Well, I was definitely, I liked these things when I was undergrad. And then, and I was reasonably good at them. And, but okay, what happened at the end of my undergrad, which formally is a master's degree in Switzerland, but it's a bit like, the end of the bachelor in the US. I mean, at least it was after, 4 years of study. I actually wanted to move a bit to machine learning. But then I read
you wanted that originally. When was that?
That was in 2006.
2006, 2007. I mean, I was just my third year of college, and I don't think I ever heard of machine learning until 2009, maybe later. I'm amazed that that this was already on your radar.
Well, somehow, I mean, yeah, it started even, a bit, my interest in machine learning started even a bit earlier. I would say.
Because were you closer to computer science, being interested in these random graphs and such?
Well, it's definitely, related. But yeah, okay, so, okay, maybe we're going to go back in time all the time. But okay, if we go back a bit, earlier, so my interest with, computer sciencey things, I think it started around the age of 13. So the way it started is my dad was a professor of nanotechnology, and he wanted to learn programming. So he bought a book to do C programming. And we did the first lessons together, and then he stopped, and I kept going. So yeah, then I remembered my, the first time I did something that I found was interesting with the program, which was I determined that our phone number was a prime number, and I was very, very excited. And then I started, getting interested in cryptography, and fairly soon I realized that computers could in principle do very interesting things if you were just to write the right source code, the right code, and that there were so many codes you could write and so many things you could in principle do. It's very easy to do a back of the envelope calculation to realize, there are more programs that you can write with 100 lines of code than, particles in the universe or things like that. I mean, even like valid programs that compile and do things. There are so many of them. And then, I started going to forums, and people were speaking a lot of neural networks actually in the early 2000s. And so I met some people on the forum, and we started a messenger group. And our goal was to do some kind of image recognition thing, but we knew, very little. We were all very, very young. I mean, I was like 16, and the other guys, I never met them in real life, but I think they were like 18, 19. I mean, I don't remember for sure. I don't even remember the names, but we would just spend our nights discussing on Messenger about things and fantasizing a bit, about artificial intelligence and things like that. So my interest dates back from, when I was like 15, 16. But then I didn't do much.
It's very interesting to me as someone who, came up, I was exposed at some point to math, to pure math, to number theory. I guess I took some programming in high school, but it was just, computer science was not on my radar.
And certainly, but it depends on a bit of luck, right? I mean,
I think it was lucky, not
I guess. But yeah, I had also, in high school, I had a few friends who were into programming, and we didn't do much together. We had discussions. We had many discussions, but it was it never really went beyond the stage of discussion, except that with a friend, we decided to do some computer programming competition together, and so we solved a bunch of problems. Somehow our documentation was not good enough so that we were not qualified for the next round. But yeah, somehow that was the only project I did with someone for a long time, actually.
This is when you were still in high school?
Yeah, like senior year of high school.
But then you went into math. In Europe you have to specialize in college, I think, more than in America.
So you have to choose at the when you start, and yeah, it was not an obvious choice to go to math for me because it would definitely have been easier to do computer science. My friend who did this programming contest with me, he went to computer science and ended up doing a PhD. And yeah, now then he worked for IBM Research. Now he's working at 2 Sigma in New York. Hi, if you ever see me. But yeah, anyway, so my parents told me I would learn more if I studied math, and I said okay, sure.
Just did what your parents did.
I wasn't bad at math either, it was okay.
Yeah.
But it was definitely less of a passion than computers back then.
I didn't know this about you.
Well, that's that's how life goes sometimes. And yeah, the college experience in Europe is very different from the college experience in America. You still live at your parents' home. You don't do the student parties so much or things like that. It feels much more like a
you know what? I wasn't invited to a whole lot of parties, I have to tell you, but
yeah, but what I mean is, okay, I understand your point, but what I mean is that it feels more of a continuation of school somehow. Like, if you don't go to classes in the morning, your parents will tell you, why are you not going to classes, right? And you just go to classes like you go to school, and it's not...
college is a big coming of age thing in the United States. A lot of people are living away from home.
Yeah, it's completely different. It's not like no one it's not that everyone lived at their parents' home when I was in college, but most people lived at their parents' home, and a very different setting.
But also you have parents who would encourage you to do math over computer science, which I have to, I want, as much as I love math, and it's my real, the math, my real passion. I wonder about that advice today, I have to tell you.
I think people in Europe live in different realities than people in America. And well, things have changed a bit, but Europe is always a little bit behind. America in terms of trends. And it's, you know, I don't think it was weird for parents in that time, like early 2000s, to think that math had a brighter future than computer science. It was not a weird opinion or a fringe one, or, you know, it was actually a fairly mainstream opinion, I would say.
Really, that's very strange to me. I can see how in some countries, that some society, they attach a lot of importance. They put a high value on mathematics. Even I know places like Iran, for example, they put people. But anyway.
Yeah, sure.
But I don't know, as a business, or even as a research direction, even if you were just going to be in pure research, certainly in terms of job opportunities. I mean, but I
mean, you're perfectly right. I mean, I think that it's just the world changed at some point, and it wasn't obvious to the people at the same time. It came at, you know, different waves, and yeah, I think Europe, in terms of technology, was, I mean, in terms of mainstream adoption of technology, was still lagging somehow behind the US. I mean, when I was at the end of high school, we had internet, but it was a new thing, and it was not everyone had internet. It was only a minority of people who had internet, and it was only in my senior year of high school that we had internet, for instance.
Oh, really? I guess, okay.
Well, I'm a bit older than you, but it's more, you know, not much. So there's, it's really, you know, a matter of perception. You know, I think that, you know, math is certainly something that Europe developed. I mean, much more so than America. And computer science is certainly something that America developed much more so than Europe. I mean, these two things are somehow obvious. And yeah, there was, you know, people didn't really believe so much in computer things for a long time. But okay, anyway. So
you worked with. I want to skip ahead to the time. How did I guess you worked with a Fields medalist and some very good math.
Yeah. No, so okay. Yeah, I wanted to tell you the story how I ended up working with him, maybe.
Okay.
So I wanted to, you know, do some machine learning because this was something I really enjoyed discussing with these guys on the internet. And then I had bought a book in a library about neural networks, kind of crappy book. But, yeah, it was saying, I mean, in hindsight, most of the things you could find in that book were misleading. But okay, anyway. Then in that book,
if you're gonna insult the book, which book is this?
It's a French book, so don't.
All right, then forget it. I love people with their other languages.
No, but for instance, you know, it would say the things that were mainstream at the time, but which are wrong. That you should take very few parameters, have only 2 layers, and a lot of things that are, you know, very much the opposite of what ended up being done. And interestingly, they claim to have good reasons for, you know, that they were theoretical groundings for their recommendations. It's interesting because it's all wrong, really. But yeah, okay, anyway. So, in that book, there was something interesting, which is that it said that the neural networks had something to do with the Ising model. And I had studied the Ising model in statistical mechanics. And so I needed to do, you know, an end of study, you know, a little thesis for the end of my studies. And so I went to some guys who told me to look at percolation because, you know, they knew the Ising model, but they told me, yeah, to understand the Ising model, you need to study percolation. And then I started studying percolation with these guys. And then I was good at this, but I was not so excited. I told them, you know, is there something that is a bit more challenging? And then they told me about this work of a Russian guy who was in Geneva. And so, you know, I studied that theorem that he had proven. And I liked that very much. I was very impressed by how deep and interesting and non-trivial it was. I like that very much. And then I wrote to this guy to do my master's thesis with him. So that guy was who became my advisor, Stanislav Smirnov. Mm-hmm. So I met him at a conference. I mean, it was close enough. And yeah, so he asked me a few questions about where I came from and what I was interested in. And I said that I liked his theorem and I wanted to work on the Ising model. And after 3 minutes of discussing, he offered me to do a PhD with him. And I said, I don't know. And he told me, well, think about it. You have 3 days to decide because I have these funds that are available for, until, until next Wednesday. So I took 3 days, and after 3 days, I said yes. I mean, I didn't have any, reasonable alternative option anyway. I mean, it was either saying yes or not knowing what I was going to do after my studies. And it looked like a good, I like the theorems, I like the guy, and I like the idea of working on the Ising model.
Sorry, you're saying your hesitation was you were still interested in pursuing machine learning or something?
I mean, among other things, but, it's like, I was in a place in the end of my studies in math where machine learning was never, so much spoken about, not more than in the environment you were in. And I had friends in computer science telling me, machine learning, yeah, it's interesting, but it doesn't work. And yeah, and then I met this guy who does something that I really like, that is really non-trivial. And I had this idea that, okay, I read that crappy book that if you understand the Ising model, you understand neural networks. So let's see where it goes. And so yeah, and then I started my PhD with him, and I worked on the Ising model as I wanted. So it was a good coincidence because he was actually he had not published anything about the Ising model, but he had a big idea about the Ising model.
What was his, just remind me, the result for which he won the Fields Medal was establishing some convergence of one of these models to some SLE, right?
Yeah, I mean, in the, the citation mentions a number of works, so some of which were works about the Ising model that were developed when I was doing my PhD. And some of the earlier works on percolation. Mm. But yeah, I think
we will have to.
He's more famous for the result on percolation, a little bit more, but yeah.
If we, I did speak about percolation with Phil, but I think when we come around to the subject, if we speak about it some more, I think we will have to, for the audience's sake, talk about what even is the Ising model. Sure. But for now, I guess I'm just hearing your story of how you worked in this field and then came around back to machine learning. But I think you must have had some sense. I have to say, I never knew, I don't know, entering grad school or even late undergrad, that I could work in something that was so active and very exciting. As exciting as I think this. Statistical mechanics and this connection to conformal field theory and SLE was.
I was definitely very lucky in that respect. I mean, I was at the right place, and I met the right postdocs before I met my advisor. I met some postdocs of another professor who were the ones who guided me, into percolation, and I was definitely very lucky in that respect. Yeah, absolutely.
This is something I think I was totally unaware of this as an undergrad. I think I might have overheard someone mention something about SLE once. I think Steve Zeldich might have said something in the or something. But anyway, okay. So you do your work in statistical mechanics. How do you view what is the math of that subject? Maybe very.
Yeah. Well, I mean, there are different kinds of math, and actually, my taste and my activity has varied over years. I mean, the way it started for me was, with discrete probability and complex analysis. and I would really, work on convergence of things. So I would like find local relations, try to see how you could, gain insight from local properties, local relations between objects to understand the large-scale features. So it was a lot of questions. Does this function converge to that function? And I became quite good at this. I became completely obsessed by this. Actually, it can get extremely addictive, and you can get completely crazy about these questions of convergence because
there's a lot of interesting questions, I think, in this subject that you can ask and probe.
Yeah. So the bigger part of my PhD, I spent it about worrying that some function may explode at some point, or may go to zero exponentially fast, and both of which would be bad. So somehow that's most of my PhD, I acquired some very good feeling about what can happen with a sequence of functions. I mean, on the analytical view of the question, besides of the physical significance of the results, was really worrying. What are the 20 ways in which a function can explode, and why is it not possible that the function you want to show converges explodes in that way? Because if it exploded in that way, you would probably feel it somewhere else. And if you felt it somewhere else, then probably the effect would propagate somewhere else. And that you already know is not going to happen because you have some, estimates that are maybe not so sharp, but they tell you already that some things cannot happen. I mean, you're an analyst, so you understand that this kind of crazy landscape that you're trying to construct of, if this converges, I can get that converges. If this doesn't blow up, then, things like that. So that was not as
I think I know some of what you're saying, even if, you're just describing generally how analysis goes through. I mean, the kind of thing you describe, I know when I first read Onsager's proof of that when in the limit, there is this, critical point, this phase transition in the Ising model. I was very impressed because, of course, any finite sum is going to be analytic, and it needs to do it in just the right way. It was very impressive to me, but I saw that result quite late, not in my time. So I didn't go in that direction. How did you get back to machine learning?
Well, I mean, I got back already when I was in New York, but then I didn't publish anything. And the question may be phrased more, how did I start publishing in machine learning? How did I start really, hiring PhD students in machine learning or things like that, or going to machine learning conferences? And the reason is I got tenure. I think that it would have been very unreasonable, by the politics of, things to be an active machine learning researcher before getting tenure. I think people would have looked upon me very badly, actually, if I had done this. And so,
and they don't mind now that you have tenure, or they look.
Some people mind, but I don't. I don't care as much.
That's.
But I mean, somehow. Actually, the timing. I had timed things, but somehow my tenure application, took longer. I mean, my tenure review took longer than was expected. It was expected to last a year. It lasted almost 2 years. And so my first machine learning paper still, appeared before I got tenure. And my tenure committee kind of attacked me on this on this Neural Tangent Kernel paper that now is a classic work. So I think that my calculation was correct. I had not calculated that this 10-year process would take so long. But it was not a good idea to go into that field at that time. Yeah,
Well,
so
made it
you know,
through,
that's one answer. The other is, you know, I just met awesome people who my PhD, my then future PhD student Arthur and my then to be postdoc Frank. I met them around that time, and so we really built something. So yeah, that's what.
Look, as long as you're doing good work, I mean, I think, look, you made it through this system, and that's very good. I clearly did the wrong thing, jumping into other fields and other kinds of problems. I had no tenure, no safety whatsoever, and it clearly worked out very badly for me.
Too early to tell. Too early to tell.
Too early to tell. I don't know. It'll be very hard for me to get back there. It's a shame though that you know, you like the kind of math, a good problem comes in front of you. You feel like you have techniques, you have the drive to solve it. You know, why can't you just pursue that instead of just, you know, you have to just publish in one field and establish yourself there. I mean,
I think more than, you know, the track record is, in the end you need recommendation letters, and then obviously an expert usually will just you know, be recommending you in one field because they are only expert in that field. And so, you know, the more papers you have in that field, the better it is for you. But yeah, I mean, I think you know, we could discuss for hours about how to improve the system. And you know, I think the system is clearly very suboptimal. Okay.
Actually, well, if you have ideas, we should come to that, because I certainly think it's suboptimal. I don't know. I haven't thought of anything good that anyone wants to listen to anyway. Let me, okay, I want to know, let's actually talk about some of the math itself of, I want to know.
So Ising model, or?
We'll get to that. We'll get to that. I think that more people out there, they are interested in machine learning. That's just a more popular thing, as much as I really do love the Ising model, and we'll talk about that too. Right. How do you, as a mathematician, view, what is the math of machine learning? Maybe I'll put it that way. And
well, you know, I mean, it's a bit too early to tell somehow.
Okay, what's the problem then? What's the problem? What do you view as, like, maybe even?
What is the math problem? I think the main problem is to define the problem. You know, I mean, the main problem is to find interesting math problems somehow. But you could, you know, there are many questions you can ask a priori, which are interesting questions. But these questions, they cannot be so easily translated into math problems. I mean, there are many questions that you're probably wondering about, many people are wondering about.
Well, how about this? You know, it was a major revelation to me, because I guess I never saw this thing that you, I guess, saw pretty early. I learned something about computer programming and how you could make a program to do a very specific set of tasks. And it never occurred to me, even if I was as a kid, you know, had the idea of artificial intelligence, it never even occurred to me how anything like that would work, how any of it. And yet, as you notice, you know, people figure out how to look around in their environment and recognize in their view, what's a tree, what's a person, what's a whatever. And this is always a mystery to me until it occurred to me, reading stuff that I guess people had figured out quite a while before, that all learning is like that, is statistical inference. Like
I mean,
of, well, okay.
All learning can be studied through the angle of statistical inference, perhaps. But
yeah, but you can take some organization of the raw data that all belongs, I don't know, either classified into some discrete groups, or there's some pattern, you know, it follows some function, and you try to learn that function from the data.
No, I agree with you. I mean, I would say, you know, definitely learning to recognize objects falls into that category. And, you know, learning to predict what's going to happen to you if you do such and such thing definitely falls into that category. I mean, you could still ask questions. I mean, yeah, sure. You know, okay, so math, okay, that's an activity. You know how to work with epsilon and deltas and whatnot. Is it statistical inference? Maybe it is, but then it becomes a bit less clear in which sense it is just statistical inference. I mean, there's many processes that you do in your brain that, you know, you could say that's probably statistical inference in some way, and definitely you can study them in that through that lens. But, you know, okay, even, you know, if you go to kind of semi-philosophical questions, you know, like what is love? Is it statistical inference? Well, then it gets a bit, you know, a bit unclear. But I would say there's a lot of things that are statistical inference indeed. And
okay.
yeah, that's
statistical inference on some level, but of course also when it comes to learning some function that you don't know a priori, or trying to guess and put things into categories as best you can. It's also, in my view, so the approximation theory, and of course the theory of computation, how to do this efficiently. That's somehow necessary. You don't ever have access to the real thing. There isn't even a real thing. It's just how close can you get with what computational resources you have.
Okay. No, of course they're very interesting. These are already very interesting questions in their you know, on their own. So I mean, somehow, you know, maybe the key word would be more than statistical inference. I mean, even though it's not a word I disagree with, I think the basic theory that underlies our understanding of what it means to learn from data is more about information theory somehow. It's about you really acquiring information about your environment through observations and updating your, you know, understanding of the world through observations. And but you could say actually all science is about this. All like the natural sciences are really about understanding the world through observations and using, you know, efficiently these observations to update the view of the world and understanding which observations to try to get. So I would say.
How do you say that is different? What do you mean specifically by information theory, say, as opposed to statistics?
Yeah, I mean, statistics, okay, you know, in principle, it's really about how you reconstruct the world from data, indeed. But if you look at the field itself, what do statisticians do? I mean, they have hypothesis testing and they have intervals of confidence. Is it really, you know, the way we really understand the world? Is it really the way kid learns to do things? I don't know. I mean, they're not doing confidence intervals and things like that.
No.
I think it falls more you know, into the point of view of information and theory, which is at least it you know, these may be two ways of looking at the same thing, but I think the point of view of information theory, if you look at the works of Shannon, I think he understood a much greater deal about what it means to learn than statisticians, for instance. But that's my take.
Really? Yeah. I guess I know that. How does it enter in? Just the so-called cross entropy loss, the idea that some observations matter more than others, and the way you measure it. This is something I really don't know a whole lot about. So if my questions don't make sense, please.
No worries. No, but, you know, I think statistics and information theory are somehow two competing ways of understanding the same question. But somehow the machine learning revolution has shown that the information theory side has kind of won this challenge in terms of understanding the world, really.
But why? So how does it? How does that come in? Other than say in the loss function or?
Well, I mean, how does it come in? I mean, when you start speaking of loss functions and things like that, you're already in the information theoretic mindset, I would say.
Well, listen, there are easier questions. Look, I guess.
No, but you know, I claim that you are closer already to information theory than to statistics without maybe knowing it. But you know, by asking these kind of questions.
maybe I'll say, look, I actually, here's an admission that I think is very embarrassing to me. It should be more embarrassing to the educational establishment somehow. I never took a course in statistics, never. And it was just, I think there was something wrong with the fact that, oh, if people thought I'm good at math, I should take calculus and not statistics or something. And I think that it's totally wrong. Totally.
That's wrong. Actually, I had an excellent course in statistics in my sophomore year in college.
I should have
liked it though, but it was excellent.
I was never encouraged to do it, and it was always seen as like, oh, this is the thing, like, oh, the people who just tabulate data or something. And
statistics is still that, actually. I mean, again, that's why I'm saying information theory is the right thing. There's very much this tabulating thing. And so at some level, it's maybe the math theory of tabulating things, but it is really,
But if you ask me, it's more rich, and it depends on calculus and probability. It's such a fascinating subject, and very practical too. People did have to figure out in the 16 and 1700s. They finally got to a point where it really mattered. They were making astronomical observations, or they were taking records of how many children were born in different places, right. And they actually wanted to know something they couldn't answer, or like, how do you, I mean, two questions. How do you fit, say, a line or a curve to data? That people in the ancients dealt with this problem and never really figured it out. They just picked the data points that they liked eventually, right? They didn't, that when they had
also fit their data. That was a popular approach then.
Yeah, they did not know how to deal with this until the 18th century, and really only around
basically,
around Gauss, I guess.
Gauss definitely.
And they didn't know like how to, it was like, is it really 50-50 that a baby is born a boy or a girl? Can you tell from the records of or whatever? And so what do you expect when you flip a coin so many times, and then can you tell from the coin flips, if you've done it enough, what the probability really was, right? So that's when people really had to deal with this problem in a serious way. And then they understand there's certain distributions that things fall into, and you can use this now in this much more, as you say, is that what's going on in a baby's head when he learns who his mother is, or what is a tree or whatnot? Well, he's not aware of it, but I would bet you that his neural architecture is set up to calculate things in such a way that it's somehow aware, it's somehow using, it's consistent with the kinds of.
I agree with you. I mean, I think, it's. I mean, babies are typically, I mean, animal brains in general, including humans, are typically, one of the big tasks is learning to foresee the future, and learning the relevant, objects to be able to foresee the future. So that's really, something that is a driving force in the development of intelligence, in all cases. I mean, why do you need to know the concept of your mother? Because knowing that concept definitely helps you figuring out what's going to happen to you in the next few seconds, whatever your situation. So that's definitely.
I agree with that evolutionary analysis, but I have to. What I want to know, I'm curious about how the brain actually works, but I'll put that aside for the moment and just say, how do we say classify images by a computer? Because that happens to be the issue that I'm dealing with now. I mean, lots of people have dealt with this, but how?
So is that the question? How do we learn? How do humans learn? Or how do computers learn?
Well, how do computers learn? And I guess I got the impression, I know some of the development of this subject followed inspiration from how people thought the brain actually worked. And I would guess, there's a bold claim, and I hope to have someone on the show someday to maybe put it to them, like, do we know, is it really the case that the brain does some version of this, of what we call an artificial neural network? It's doing it now. It won't be exactly the same because the brain doesn't operate on floating point in the same way, and whatever, right?
Yeah, yeah. Okay, great question. I can elaborate on this.
Yeah.
So, I mean, you know, neural networks, or I mean, machine learning, I mean, deep learning algorithms, there are always two elements that are, you know, are involved in the description. There is the architecture, the structure of the neurons, which is usually a fairly static thing. And then there's the way you train the neural network. And the second part is not to be neglected at all. It is crucial. Okay, so there is definitely evidence that there are similarities between the architectures of convolutional neural networks and the architecture in the visual cortex, which is a tiny part of our brain, but you know, the part that allows you to see, and so related to that, to your question. So there are definitely similarities in the architecture, and you know, probably one could, you know, even argue on some kind of equivalence. And I am not enough aware of the mathematical works, you know, towards like establishing such an equivalence of architecture. But there's definitely, you know, intuitively, you have some equivalence.
I bet it's a very interesting question, and but I would also guess that there's no need. It's not like copying the brain is the right approach to building an artificial neural network.
No, the same way that you know, for a plane to fly, it doesn't need to have flapping wings. Yeah. Right.
Although actually, that's
that would be nice too.
That I've always wanted to see if you could build a non-fixed wing aircraft. And I mean, I know they have.
I can send you a YouTube link after the show about this. But yeah. No. So that said, you know, the way the training, learning happens. Once you have the architecture, there's a training and learning. And these are at least superficially very different. But it still remains to be understood whether, you know, to what extent they are different or similar. But superficially, you know, the key word for machine learning is gradient descent. You optimize things with, you know, variance of gradient descent. By computing derivatives, you need to know Newton's calculus to do learning, while the brain doesn't seem to know so much about that concept. So there are definitely differences.
I don't. Yeah. Okay. So we'll leave that as a curiosity. Why is it not? Okay. Maybe I'll just put this out there. That here's a silly question. Why is it not a problem of a subject that I happen to be very enthusiastic about now, approximation theory? So in my view, you can couldn't you look at this problem as saying, well, there is some very fancy, very sophisticated function that does your classification, or that sorts everything on this very high dimensional space of all possible inputs. And you have all this, you're trying to learn that function in some simpler way. You have some data points, and you just want some simple thing that sort of weaves between those data points in some nice way.
Do high dimensional interpolation.
Yeah. So why is it not? I mean, okay, I'm familiar with this idea of overfitting. That must be the reason. Why don't you just?
Why is it not a good idea? I mean, I will tell you very simply. It is a good idea, but in itself, it's not clear. It's not really an idea because you have so many ways of interpolating. Okay, so maybe you can ask me, why is it not a good idea to do piecewise affine interpolation? And I would not even rule out that it's, you know, that it's a good idea. Maybe it is a good idea. It has not really worked, you know, as well as neural network methods. And maybe one reason is, you know, lack of symmetry. So I'll just tell you what it means is, you know, I mean, okay, imagine that you have an image of a car, and then you learn that this is a car. So you try to fit Now you just shift by 1 pixel up and 1 pixel down your image of a car, and it should still be an image of a car. Yet, without, if you view your image as a collection just of numbers, you have not learned this translation invariance, for instance, then you're not able to tell that the shifted picture is a car. And probably if you do a linear interpolation, that it doesn't work so well either.
That's
a simple answer why linear interpolation doesn't work. But interpolation is a good idea, and neural networks do perform interpolation. Actually, maybe that brings us a bit to our first result in the topic, which was to demonstrate that actually neural networks do perform interpolation. Interpolation is good, and overfitting is not a problem. Is not a problem that neural networks, how should I phrase it, do face in practice. Neural networks do interpolate through the data points they are fed with, and they are able to generalize very well. And so there's no contradiction. And maybe the strange thing is that you've always been taught, if you had studied statistics in college, you would have learned that there's a trade-off, that you cannot at the same time fit the points and at the same time generalize well. But there's no trade-off in machine learning. That's the magic, is that there is no trade-off.
Yeah, why is that? This is something I've
Well, I mean, this remains a mystery to some extent. Why there is no trade-off? Why, and of course there are tasks for which it doesn't work. You cannot, fairly obviously, no one knows how to train a neural network to recognize a prime number. An image of a prime number. So
I'm very skeptical of some of
there are many things that neural networks cannot do, right? I mean, they cannot learn to recognize prime numbers. You could argue, well, but animals can't either, and that would be a fair point. But okay, there are things that neural networks cannot do. But what is maybe miraculous is maybe something about a world. Why is our world so learnable? Right? Why are these kind of complicated things like, distinguishing what is a cat from a dog, which, boils down, if you think back of, basically these were initially 2 cells when they were tiny babies, then they grew, and they had just difference in their DNAs. And this difference in the DNAs, yielded some macroscopic things, and the neural network is able to identify that feature. And that sounds like a miracle. You can do it just on the basis of this very, very nonlinear function of the DNA, which is the evolution of nature, of the animal throughout its life. But yeah, it's non-trivial, and it requires some fine understanding of what our world is made of. But in alternate universe where things are crazy, neural networks cannot learn things. That's.
I don't know if you need the, it'd be very nice to, can you learn just from what the DNA is, what will be the features of the creature?
Oh, I'm defining what is a cat and a dog in the end, right? What I was doing is define mathematically what is a cat, what is a dog. It's 2 creatures with the different DNA, with significant features that have led them to become to have different appearances. But I tried to frame the problem mathematically, right? That you try to compute the inverse of some function. It's crazy that you can compute the inverse of this function by just looking at a few examples. But that's a mystery about the world.
Well, maybe to this I'll say that the other half of this revelation, I don't know what you'll think of this, that learning is in some sense statistical inference plus some computation, is also, I think, in part a resolution, or at least a view of a very old philosophical problem of definition. In math, we like to work with very precise definitions. This thing is definitely, we know exactly what we mean when we're talking about a group, a prime number, whatever, a triangle. Plato dealt with this problem too, you know, but it's very hard to say what we mean when we talk about a chair or a poem or whatever. And yet those are the things that make up real life. And we don't encounter the mathematical things. They're somehow abstract and ideal, but the real things, it's very hard to pin them down, but we all think we know what we're talking about. And that's exactly, I think, because we all form our own view of these things built up from examples that we train to recognize, built from those examples. And actually, some of us have seen very similar examples. There will be a substantial overlap, but not total overlap between that concept and each individual person. They trained their architecture differently.
Absolutely. No, I think you're right, and it may very well be that, you know, the tasks that we ask the computers to do nowadays are those tasks that we with our neural networks are able to do, and so there's maybe just a nice subset of all the tasks that can be done that are tasks that can be performed by neural networks trained with a, you know, limited amount of energy. And yeah, we just found architectures that maybe there's a general equivalence principle that, you know, a task that can be learned by a neural network can be learned by another neural network or something like that. I mean, provided they are big enough, they have enough data. Maybe there's you know, that still, yeah.
I would like to see, yeah, some theorems like that, and you know, how complicated is a problem, and if the problem is that complicated, how much data do you need, and what sort of architecture do you need in order to train? You know, you want enough accuracy. What is it going to take? Are there better activation functions between the layers for this task, et cetera, et cetera?
Maybe it doesn't matter. Yeah, very good questions. I think, yeah, what did I want to say? I think it's definitely not out of reach to prove interesting theorems. Actually, something that we are you know, planning to study in my group is eventually, but we, you know, we need the right model of the brain, of the biological neurons. But so what we did was to study what is really the learning performed by neural networks when they are large. So, you know, in practice, the neural networks are fairly large.
And large meaning lots and lots of neurons in a single layer, but not, is it multiple layers?
Maybe an infinite number of layers, or maybe many layers, but many more neurons per layer.
Okay.
I mean, this is really the structure of the visual cortex. This is really the structure of working neural networks. I mean, working artificial neural networks. So these are, you know, definitely common features. So we were able to understand reasonably well. I mean, and it's not like completely over, but we understood some limit of neural networks as their width grows, which describes fairly well what artificial neural networks are doing. So we understood it mathematically in terms of, formalism you could liken to Hilbert space formalism. But, so that's the thing we are famous for, you know, having constructed this neural tangent kernel, which is a kernel which describes what neural networks learn from the data that they observe. And, you know, a project that is ongoing, but honestly, we lack people to work on this at the moment. But at some point, we'll have people work on this.
Yeah, I'm amazed that you lack.
It's the equivalent for models of biological neurons, right? And a problem there is, you know, there are many models of biological neurons you can find in the literature, but you need somehow to find one you're convinced is kind of good. And you know, there comes a problem that is not a problem of math, but more a problem of biology eventually. You know, what is the good description of, you know, a bunch of neurons, biological neurons? But okay, you know, conceivably there could be some study of this infinite width, also limit of biological spiking neurons. And one could get a clearer insight into the similarities or differences between the way they learn. You know, if they're fed with the same data points, how different are their predictions outside of these data points? And this is a good question. I think this is a good question. And it's not intractable.
Data
But,
point.
okay.
Can I? Oh,
yeah, go ahead.
Can I just ask? Maybe this, if you establish some result like that, there will be convergence to something if the neural network is big enough. That sounds to me is that it sounds a little bit like, say, the Weierstrass approximation theorem. Is that like where you have a space of functions? It's enough that in the limit that you can represent any function sufficiently closely by a function.
Well, not exactly, but
no, you okay,
but not exactly. But you know, okay. So the Weierstrass, there's a theorem about universality of neural networks that is very much akin to the Weierstrass theorem.
Okay.
And that theorem is fairly old, and it's the reason for the nonsense I would read in the book of neural network that I read when I was in beginning of college. And that result is indeed that with the correct weights, with the correct parameters, you can approximate any function.
Okay. Yes.
That is correct. But you know, there are two problems with this. One problem is that it's non-constructive, as is the Stone-Weierstrass theorem. It's always based on compactness ideas and.
Well, there are constructive proofs using kernels, but they're very bad for the degree. They're very inefficient. But yeah.
Well, yeah, but. Yeah, okay, but so somehow, okay, now you're going to Stone-Weierstrass, but I was saying that the results for the, you're right that there may be semi-constructive proofs for Stone-Weierstrass depending on the class of function you're looking at.
Yeah.
I mean, again, so, you know, it's a function of the class of functions you're looking at. And of course, if you look at polynomials, then there are constructive ways, but, you know, then it's always just as constructive as the kernel you get. So, but okay, for neural networks, so there are such results, but there are two problems. One problem is you have no idea how to find those parameters.
Yeah.
And the other is for a given collection of data points, first you have no idea a priori whether there are, you know, how many parameters you need to fit, but also there are many ways of fitting. Maybe with the same number of parameters, there are many ways of fitting. And which one is the more correct one? Which one is the one that will generalize? So, you know, there are these two problems, and somehow, you know, these universality theorems don't help. That's the message. Okay. So our result is more, you know, what are you going to do if you train a neural network with the gradient descent? Why is it going to converge? Why is it going to really fit the data point? The data points, and how is it going to predict things outside of those data points? Can you compute that?
Yeah.
And the answer is yes, basically. You can compute that, you know, fairly explicitly, in the sense that if you give me, I don't know, 100 layers, and you tell me I want to take the ReLU activation function, and you give me Mathematica, I can get a semi-closed formula to explain to you how, given the data points, you're going to predict such and such thing about a previously unseen data point. So that is, you know, what our result was about. And so it gives at least.
Can I just, the kind of result that I'd really like to see, though, maybe the reason so your result is not.
Tell me what you want, and like maybe we'll realize your dreams.
I want to see a result that actually, because what you need for computation is, well, how close are you at a finite size? I want an error, you know, that kind of error.
Well, I mean, so there have been definitely results on that. But okay, I don't want to oversell our results or those results. So there are results about that, and you know, from a mathematician's point of view, they are reasonable. These results, they will tell you that if your width is maybe the cube, or a bit even less than compared to the number of data points, then our result, you know, really applies, and you know, you're very close. But again, from a mathematician's point of view, it's good because it's just a polynomial, and a fairly low degree polynomial, a cube. From an application standpoint, it's not the answer, because Neural networks, they don't use a number of parameters that is cubic in the number of data points.
Yeah, that'd be very...
Maybe they use more parameters than data points. It's not the cube. And so there may be very well be something interesting that happens in intermediate regimes. And okay, and you know, yeah, there's a lot of people working on these questions, and these questions you do see some progress. My intuitive feeling is that the hardest remains to be done. Okay, about that question, and you're pinpointing to exactly the hard part of the harder part of the question. But you know, we hope to get there one day, right? We're not there yet, but somehow there was already some progress. And from the point of view of someone who is not very connected to reality, then our result is definitely good, very good. If you need just a cube, you know, it's like if you said P versus NP, if you can solve the problem with a cube of the size of the data, maybe you cannot solve your problem in practice, but that's already pretty good. So, you know, it depends a little bit on one's point of view. My desire, and maybe yours is the same, is really to understand the practical world, and not to have things that are only true if you have a gazillion parameters, maybe that, but things that are true if you have a billion parameters. But yeah.
That happens to be my preoccupation now, that no one's paying me to prove theorems, but I have to have a business that, you know.
Yeah, if you need a business, then it's you're not okay with having a big O. Even using the big O notation may not be okay. You may want the control over the constant also.
That's right. Of course. I mean, of course, proving a different growth is probably helpful, but yeah, control of that constant. You got to be, approximation theory forces you to know, you know, I want this size, what's the best I can get at this degree? Because that's what you'll actually compute.
But you know, okay, so a result gives an idea, okay? And it's not, you know, practically useless. It is useful practically, because you can still compute the approximations of this object, see how they, you know, see the trends as your size of the network grows, extrapolate from the trends and do things. I mean, people do really use object, but yeah. So you're right that we have not understood to this point completely what neural networks do.
Are you saying you can use your the theorem in your paper to say either train or perform the testing of some neural network in a different way? You either avoiding some of the
well, more for the following, you know, there's, you know, there are different ways in which it is used. I can, you know, I'm not sure I can comment on all of them because I'm not aware of most ways in which it is used. But for instance, you know, Google has implemented this neural tangent kernel in a Python package, and they're using it. You know, there are people working at Google who compute the neural tangent kernel of their product. You know, their at least soon to be in production, perhaps neural network. So it's not something that is completely hypothetical. It's fairly simple actually. But you know, one thing you may want to do is neural architecture search. So you would like to find what is the best choice of width for your network, right? And so what you can do is you can just
can we just say width is the number of nodes
per layer.
Nodes per layer. Okay, yeah.
Yeah, but okay, you also want to find the correct number of layers. You also want to find the correct number of layers as well.
Yeah, this is something this is very unclear to me how people make these decisions. It seems to be very experimental.
But you know what it is? You're right. It is experimental, and that's fine. You know, that's fine.
Could you reduce the goal is somehow to get the highest accuracy, but with the least computation costs? You actually want to condense. You want to have few layers and fewer whatever. If you used better activation functions, or maybe a better version of the convolution where you only looked at certain things at a time, this would help you.
Who knows? There are so many possibilities. Not, you know, people don't know everything. But you know, I you know, okay, just a comment, and then we go back to this question of neural architecture search. What has appeared so far in practice, and that's you know, something that is a bit disconcerting maybe to a theoretician, is that for different sizes of data of the data set, different architectures are better. And so, you know, well, which is fine, but it may hint at the fact that there is no better architecture. You know, it just may depend. But then there's maybe a better function of the number of data points. There's always a better something, right? But that is not known, at least not known to me. I would guess that big companies like Google do have a lot of data on what worked and what didn't work about training which kind of architectures. And I would guess that they don't share that data so much because it's actually extremely costly to acquire that data. It's the amount of, you know, the price in electricity you need to acquire this kind of data is ridiculous. Well, yeah, and I don't know to what extent it's kind of put in writing and, you know, clear. But okay, anyway, so there's the question of what is the best architecture, right? And one key component of that, of such choice, is the size of the layers. And what you could do is to do machine learning on machine learning, and that's, you know, this auto machine learning thing. So you could try to try to train with a certain size, see what result you get, increase a bit the size, see what result you get, and then feed that kind of data to a neural network and ask the neural network to predict, you know, performance for architectures you have not trained before. Okay, but so it would still be very helpful for such architectures if they predicted the right asymptotics at infinity, right? It's a good way to add a very important data point to your neural network, to your meta neural network, which predicts the performance of architectures. You know, we know what is the limit. And so this is actually the hardest data point to get because you would need a lot of compute power to get that. So you know, it definitely, you know, gives some. It can definitely be useful to improve your prediction of the performance of an architecture.
But is this something that you can actually carry out? I took an online machine learning class, and even my computer, you know, had to run a long time just to classify some images.
Yeah, of course. But okay, so that, I mean, that's kind of the point is, you know, when you have really too many parameters, you cannot train. And that's where our results that's becoming relevant, right? Because we compute analytically what the limit is. So you don't need you don't need a neural network, but you can. But you know, if you have this neural network which, you know, is fed with architectures and predicts the performance on the basis of the architecture, you can give it a very important extra data point or collection of extra data points, which are how well it will perform when the size becomes very large. And that data point is extremely hard to acquire. That's what I meant, right?
I see.
You don't have an analytical approach. But it's mathematics. You know, as often, you know, in the world, you know, the things that are harder to compute, you know, by brute force are sometimes easier to compute by analytical means. And this is not unheard of in math. You know? It's easier to compute an integral than to compute a sum, even though a sum is you know, easier for a computer to approximate. Right?
Are you saying so? So what your result helps you to do is that you have to do some finite computations with your finite neural network, but then this, what you say, well, here's what it would come out if your network was much larger.
It was much bigger, yeah. But you know, okay, so you trained your neural network to fit, you know, a number of the, you know, size, maybe 100, 1,000, 10,000. Maybe you stop there because it's too big after that. But then you can tell also the neural network, hey, but you're going to do that performance if your size is 1 trillion, right? You're able to say that, and that definitely helps it fit better.
I see.
You know, that's
yeah, okay. That's interesting. Let me ask you, did you ever find out, or are you ever convinced, I want to pull this back around, you really reached the limit of my machine learning expertise here. Was the Ising model at all related in the end to these neural networks?
The methods, not really. The thinking with discrete probability definitely is of some help, though not strictly speaking necessary. You know, many of the important ideas came from my PhD student, who is a very brilliant kid and who definitely knows what the Ising model is.
Ideas about this neural tangent kernel.
Yeah. He definitely knows what the Ising model is because I taught him. I was his teacher. That's how he met me, right? And he also knows a bit about conformal field theory because I also forced him to take my class on conformal field theory. But is not someone who
I think I took your class.
is an expert on those topics, right? So yeah, I mean, then further machine learning results that we had about you know, they are not as popular, but I think they're interesting as well. About you know, things that are a bit like neural networks, but simpler in some sense. They use complex analysis in the proofs, and so definitely, you know, knowing complex analysis is helpful. We definitely didn't have to learn complex analysis to do the complex analysis part in the paper because we knew what it was about.
You say in something related to machine learning, you're using complex analysis?
It's not so surprising. I mean, generating functions, I mean, are things that I use complex analysis. So, if you want to study the spectrum of a random matrix,
yeah,
you know, this kind of things come up quite often. I mean, one of the, you know, once I was at the doctor's in New York, and I was obviously not very ill, so he has started asking me questions, you know, but what is complex analysis really useful for? What are complex numbers useful for? And yeah, but it's nice. It was a nice question, and of course, yeah, it made me think. You know, what I said is, you know, the most real appearance of complex and universal appearance of complex numbers is as eigenvalues of operators or matrices. You know, this is really something I cannot do without complex numbers. I can do electromagnetism without complex numbers, but I cannot do diagonalization without complex numbers. And yeah, I mean, okay, anyway, so to study the spectrum of random matrices appearing in machine learning.
Well, you'd have rotations instead, right?
Yeah. No, but you know, you could, of course, but you know, the complex numbers as numbers, they appear really intrinsically in linear algebra in the spectrum. You know, yeah, well, okay, anyway.
Well,
so,
I mean, they first appeared when
complex analysis for random matrices. So.
People were trying to just solve polynomial equations, right? And they came up.
No, but the numbers are as numbers, you know, not as auxiliary things. They you know, the spectrum of a matrix is really the object to understand the matrix. Yeah, I would say this is the most kind of it's the hardest use of complex. It's the use of complex number that is the hardest to get rid of. You know, I can get rid of complex numbers in quantum mechanics if I really want. I can get rid of complex numbers.
Wait, there's an equation there with an I in it, the Schrodinger equation.
Yeah, but you can get rid of it. You can get rid of it. I mean, it's not like fundamentally complex.
Well, what about, I mean, fundamentally complex here. Okay, well, what about conformal mappings?
I mean, well, you could view them through the angle of geometry, through the angle of circle packings. And in principle, I mean, again, I'm not advocating to get rid of the use of complex numbers, but but you know, if you ask me where is the place where complex numbers are the hardest to get rid of, I would say linear algebra. But you know, it's a slightly philosophical question, and we can debate for hours about it.
Well, okay. How about, well, how does it come up? Let me ask you about, can you explain the Ising models? I may say Ising. Can you explain what it is, maybe where complex numbers come up there? Is your work there, or is this?
Yeah, of course.
Okay.
My pleasure.
You're here to tell us.
So the Ising model, it's a model that lives on a graph. I mean, mathematically it lives on a graph. And the graph physically is supposed to represent some atomic structure. And so it's a model traditionally of magnetism. So in an effort to understand magnetism, people postulated that there would be tiny magnetic dipoles living, you know, on a molecular lattice. And so simplified
of atoms at each point on a graph.
So you know, atoms often, you know, in solids, atoms form lattice often. And so you imagine, you know, it's a very big simplification of the world to think, okay, maybe a magnet is made of lots of tiny magnets. Okay. And then what are the tiny magnets made of? Well, that question is left to quantum mechanicists, right? But okay, so you have lots of tiny magnets, and then they have short-range interactions. So a bigger simplification, a further simplification is to say, well, maybe each magnet is only going to interact with its neighbors on the lattice. And then, then you ask questions. So one question is, can you explain the emergence of magnetism as a global phenomenon from such a microscopic model? And the answer is yes, you can explain something. So what do you want to explain about magnetism? A key question about magnetism is the onset of magnetism in magnetic materials as the temperature of the material goes low enough. So if you have a piece of iron, it's very hot, it actually can't be a magnet. Yet if you cool it down, and maybe you cool it down in the magnetic field, but you cool it down, and then it can become a magnet. Okay, so can one explain this relationship between magnetism and temperature? And the answer is the Ising model can definitely explain such a thing. By modeling the temperature, you know, mathematically as a strength of interaction between neighboring atoms.
So what you're saying, each one is some magnet that's oriented some way.
Some way, yeah.
Simplify up or down, and they don't.
Well, okay, so that's the Ising model. But okay, so you know, a priori you just think, okay, maybe a magnet can take whatever direction it wants. But then there was some further simplifications in the effort to understand magnetism, and it's related to the quantum mechanical nature of magnetism. So you can you know, observe, you know, you can study just the one component. The so-called spin of the atoms along just one direction. And so then that gives the Ising model, which is the somehow simplest model of interaction of random objects living on a graph. But so in the end, they can just take two values.
Right. So, but just to be, so the idea is that each atom on this lattice, you know, it's oriented some way, up or down.
Up or down. So that's the further simplification that the Ising model makes. It's that they are two possible. But
the whole piece of, you know, the material, whatever it will be, will only be magnetic if there really is some strong, you know, a strong proportion are all oriented in the same direction, right?
Right. So the question of global magnetism, as you said, becomes translated into the question: is there a clear majority of atoms that choose one direction over another? So for a clear majority to emerge, you will need this local interaction phenomenon to be strong enough so that you know, you have a collective behavior that emerges where one guy influences its neighbors, which influence their neighbors, and so on and so forth. And the influence does not die out after a few steps. It keeps going. And so, of course, whether this influence, you know, of course, from our point of view now, it was not obvious at the time of Ising, I guess. But of course, this interaction, whether it dies out or it doesn't die out, depends on, well, how strong the interaction is and how many neighbors you have. So it turns out that in one dimension, you need essentially an infinite interaction strength to get an alignment. But in dimension 2 and 3 and higher, there is, well, that's where we arrive at the so-called phase transition, where there's a critical value. And if you're below that critical value in terms of interaction strength, you don't have this you know, clear majority that emerges. Basically, you get 50-50 plus tiny variation, but of the spin, so of the alignment. So you don't get a global alignment. You just have this 50% up, 50% down,
above a certain
resulting large scale effect. While if you're above that threshold, then you have a global alignment.
But
so
that means below a temperature.
Well, then the interaction strength is understood to be the inverse of the temperature. And
yeah, right, yeah.
So yeah, one usually speaks of temperature. Indeed, to close the loop with my introduction about magnetism and temperature, I'll just say that the interaction strength is understood to be the inverse of the temperature, in this model. So okay, so that's a nice model, and you can do simulations of this model and stare at them like I was when I was a grad student. Just stare at them for hours, and looks fascinating. There is this competition between phases and things like that. And but essentially the thermodynamics, the global things were actually understood by Onsager in the 40s, and so he was able to show precisely that a phase transition arises at a certain point in dimension 2, from which you deduce that there is a phase transition in any higher dimension, but he didn't care so much about this. But
so he was able to prove there was in all higher dimensions. Is that right? I mean, I imagine that the one that maybe people care about is 3.
Well, I mean, it's true. Well, okay, so establishing that the phase transition exists in higher dimension, actually, to be honest, was already obtained 10 years earlier by Peierls, not by Ising himself. Ising himself wrongly conjectured that there would be no phase transition based on his analysis of dimension 1. But Peierls, a very brilliant chemist, who's maybe known also for works on the Manhattan Project, I think. He proved that there is a phase transition using a very qualitative argument. Okay, what Onsager did was he identified very precisely the nature of the phase transition in dimension 2. He was able to perform a computation that no one was able to do, and even to this day, very few people, if any, can reproduce with the method that Onsager found. Actually, his detailed computation is a bit hard to find, I think. Online, you cannot find it.
That's right. I think there's this fantastic book that my advisor showed me. What's it called? Mathematical Statistical Mechanics or something like that by Colin Thompson.
Okay.
And that has an appendix with Onsager's proof.
Yeah.
I might be getting the name wrong. It's
but yeah. No, actually, I should check it out. I mean, somehow anyway.
And I believe also, I guess Palmer's book must have some version of it, a more modern.
So to this day, it's not clear exactly, how much we know of Onsager's work. I mean, by we, I mean the newer generations. I mean, because there are things that, for instance, my advisor in one of his papers, he cites a paper of Onsager that is impossible to find online, and it only can be found apparently at the library in Yale, where Onsager was professor. And so I've never been able to see that paper, though one of the 2 results I'm famous for in this Ising model work is a generalization of the work of Onsager. So I would like very much to read that, but okay, I've never seen it. And okay, so anyway, Onsager, he devised a number of methods. So basically, he introduced he formulated the questions of interest in terms of the trace of a high power of a certain matrix. Like many questions in physics can be translated formally into such a question. And what he was able to do is, when you want to compute the trace of a big power, you want maybe to diagonalize the matrix. So he was able to diagonalize this matrix. That work is crazy because there's a number of changes of variable, of decompositions. But in the end, it's just a change of basis. But the change of basis is so complicated because that matrix is of a size that depends on the number of atoms in your lattice, and it's exponential, the size in the number of atoms. But okay, anyway, he was able to extract the spectrum, to approximate the limit of the spectrum, and to get a lot of interesting quantities out of this. So not only to determine the phase transition point, but really to determine the shape of various quantities. And you know, when I'm saying that we don't know everything, for instance, he has this famous formula, which is now called the Onsager-Yang formula, which he provided, which he never provided the derivation for this formula. It was only Yang, almost 10 years later, who came up with a very complicated derivation for that formula. That formula you can find in the Painleve book, indeed. But, yeah.
The magnetization.
Magnetization, indeed.
Yeah. And does that also? I mean, so you were saying that the Ising model does predict this phase transition. Does it also? Is its what it tells you about the magnetization? Does that also accord with experiment?
Okay, so then there's the question of experiments. So I mean, okay, so then there's the 2D model, which I spoke about, which was Onsager's work. Then there's the 3D model, of course, and then there are real-world materials, right? And then there are real-world experiments. And so what can I say? I think that if you do a real-world experiment, your underlying model is never exactly the Ising model. So you're never going to get exactly the result that you obtain mathematically. Then you get something fairly close.
But there's no reason to expect that. You're right.
Depends on your standards, right?
I see. I'm just wondering whether that.
I mean, you get a curve that looks the same to the naked eye. Sure, you do. You know, yeah, it's okay.
But
so
can they
complicated question, but yeah, okay, yeah. I can
actually take 2D. First of all, I wonder, can you do that? There really are these 2D materials that people work with today, right? Like graphene.
Yeah. No, so I mean, and then there are several, questions. So I think there have been. So there's 2D materials and there's 1D materials. And the 2D Ising model, for instance, is both relevant to 2D materials and 1D materials. But that story was not really understood by Onsager, but the understanding of it came later. And one of my research projects is still related to explaining one experiment, actually, about that relates to an Ising model question. Okay, so lots of things, but okay. Why 1D models can be understood in terms of 2D models? Well, because that's an understanding that came in the second half of the 20th century, but quantum mechanical models in dimension D can always be recast. Quantum mechanical model in dimension D can always be recast as in terms of questions about probabilistic models in dimension D+1. So basically the time becomes an extra dimension, and you can read
something about this.
Quantities about, quantities about objects in dimension D, quantum mechanical objects in dimension D to probability objects in dimension D+1. For instance, okay, I don't want to take that side road too much, but for instance, at CERN, the results about quantum chromodynamics or Higgs boson and things like that, ultimately what you check things against, you check them against simulations of something. And so you have a 4-dimensional simulation, statistical mechanics probability simulation in the end, that you check, that you use to get some ideas about scattering amplitudes and go back to the experiment. So in general, you can do this. So if you want to understand so-called spin chains, which are 1D materials, and so with quantum mechanical spin chains, so they need to be very cold, etc. You can rephrase questions about scattering amplitudes. So you can throw neutrons at an object and see how what goes out, and the statistics of what goes out can be related to the statistics to some statistical question about an underlying 2D probabilistic model, which in some cases will be an Ising model. Okay, so there you can check quite a lot of things, and things check out quite nicely. But again, this is like real science, so you need to be tolerant to crazy amount of noise in your data. And, you know, when I see these papers, I will not say, I'm not myself completely convinced that this is definitely the explanation. It's definitely, you know, you get things that are not obviously incompatible, whether they are really the explanation of, it's something that, you know, I guess real physicists, they're able to tell, but it's not so accurate that you can say, oh yeah, if you're an outsider, oh yeah, sure, that must be the explanation, right?
Well, I guess I'm not, yeah, physics papers are a little bit tough for me. Okay, there's a couple of questions I do want to ask though. That's interesting that you say that what do they check it against when you really have to do something? It's these statistical mechanical models. I didn't know, I wasn't aware of that. There was a...
That's something that, in addition to information theory, that's something that should be taught to everyone. You know, what is going on with particle physics? Is it just drawing the Feynman diagrams on the blackboards? No, it's actually running Monte Carlo simulations of some precise, you know, probability model that you could explain to a high school kid if you wanted, because it's very simple and it takes a huge amount of compute power because you need a 4D lattice. So obviously, you know, and it's very simple, but it's never explained, I know.
I see. Yeah, it certainly it wasn't
not explained in quantum field theory either. In the courses of quantum field theory, it's not explained either.
Well, okay, so there was a thread to your work and maybe also the work of Julien Dubeda at Columbia that seemed to me to suggest that a lot of the mathematics, a lot of the formalism of quantum field theory, which was always sort of strange to me, and you know, there's all these questions whether it's rigorous, whatever. Does it even make sense? You know, if you just look at these statistical mechanical models and you start with some finite model, some probabilistic model, that makes complete sense. And then you take some, you know, the limit.
I mean, at least to the young people. Huh? For instance, I showed this to your advisor, the statistical mechanics model. Not that it will not make as much sense necessarily as, you know, some abstract thing.
I
mean, it's really a generational thing. I mean, yeah, for you, for me, it's obviously much simpler to understand the statistical mechanics. But I will not say that it's true for everyone.
But at least it held out the promise of actually giving a solid foundation to a number of ideas, all these ideas,
absolutely,
integrals and whatever.
That's why Wilson got the Nobel Prize. Okay.
That's why who got the Nobel? Wilson? But
I mean, it's not named in those terms, but it's basically about this, that he got the Nobel Prize. So he got it for renormalization group, which sounds like an abstract thing, but basically he got it because he showed the equivalence between statistical mechanics models and quantum field theories. He showed how that equivalence could be obtained in principle by physicists' standards, which are already, you know, it's already better than nothing. But again, that was transformative. And, you know, in hindsight, it looks a bit obvious that you can hand wave. Of course, you can hand wave that, yeah, statistical mechanics models and quantum field theory. Actually, if you understood both in the right way, you can just hand wave that they're the same. But, you know, the very reason we understand this connection is because of Wilson's work. So that was really transformative. Yeah.
But as a mathematician, Wilson never, you know, took limits of discrete.
And there's still many, you know, it's very vague on some level, the analysis. But yeah, okay, so that's what I got excited about when I was at Columbia. And, you know, there was a bit this possibility of doing maybe the analog of artificial intelligence to intelligence was to construct artificial quantum field theory, right? Some quantum field theory you can run on your computer. that was the idea. And somehow, well, this is a hard project, and well, it's worked to some extent, but it's a very complicated project because there are many quantum field theories, And and it gives you a lot of sweat, and proving that things converge, it's not easy to do, but getting a good, already getting a kind of well-defined formulation of what thing is what. It's already valuable, and it cannot be found in most books, if any. Which is the reason why, okay, sorry to be the typical YouTube interviewee. I can advertise that we will have a book coming about this question, probably in the spring of next year.
An actual book you're writing?
I mean, because I gave lectures at NYU a few years ago about the conformal field theory and how it comes from the lattice.
I'll be very excited about this.
Yeah, and I kept postponing. It turned out to be very hard to write, even if you're willing to say, I will assume that this is true without proving it. Even if you're willing to do that, it proved very hard to do. But 5 years after, almost 5 years later, and thanks to the help of one postdoc and one grad student, I think will be ready to ship the book in the spring of next year.
That's very good. When you say what converges to what, you're talking about something like the spins on the lattice, and you take the limit as the lattice gets.
Yeah,
or something.
And lots of quantities. In the end, a lot of functions converge to functions.
Yeah. Okay.
And in some cases, it's very easy to get the intuition why it's true. Yet it's very hard to prove, right? But okay, so even if you're willing to jump these steps to say, well, okay, let's put this as a conjecture because I have no idea how to write the epsilon deltas here, but let's write this as a conjecture. Even if you're willing to do this, it's not easy to connect statistical mechanics and a quantum field theory. But basically, it's what we aim to do with this book. At least we aim to do this in a generality that is large enough so that the imaginative reader can try to apply it to whatever quantum field theory they would want to understand. Of course, it's not the whole story because we focus on 2 dimensions and there are things that are a bit different in higher dimensions. But already, I think it helps a lot. And personally, when I read a quantum field theory book, I don't feel lost. And it's because of the research we've done underlying this book that we was going to come.
Oh, that's very good, because I do feel lost. That really was a barrier for me in physics. Okay, I have a question, and I don't know. This is just my own question. I don't know if this is good for the show. I'm very curious about these Painleve equations and tau functions that come up. They do come up, right?
They do, but that's very specific. That's a miracle, some very delicate piece of math. Indeed.
I see. Well, it occurs to me, here's a place where you can't get rid of the complex analysis there, right? I mean, these things are.
I mean, okay, it's specific enough. I would not deem it like fundamental to anything, but yeah.
Okay, but they've come up.
Agreed. 100% agreed. At least I'm not smart enough to get rid of the complex analysis there.
I'm just saying that it's something I've seen and I've never really understood in the context of the Ising model. I've never wrapped my head around.
It's a very beautiful thing. So my first PhD student, he did his PhD on this question.
Oh, really?
Yeah. And so try to simplify the approach. To simplify the approach to the connection between Painleve and Ising model. So again, the background is there.
Can I just say how it comes up to me? There's this there have been these 2 papers in the past 2 years by this team, this guy Crowdy and Anselmo da Cunha Nelson on conformal mapping, on finding the accessory parameters of conformal mapping of polygonal regions.
You mean Schwarz-Christoffel mappings? Schwarz-Christoffel mappings, you mean?
What name are you?
Schwarz-Christoffel mappings?
Yes. Schwarz-Christoffel mappings. That's right. And even mappings between regions with circular arcs. I mean, I think that these guys have I haven't heard anyone talking about it, but they've really answered such a major question that occupied so many of the great 19th century mathematicians, Riemann, Schwarz, Poincaré, Painleve, Fuchs, all these people were trying to figure out, well, what is, once they learned that you could conformally map, these the disk to a polygon, right? They tried to write down what that map was, and they have this general form for it, but they're missing these so-called accessory parameters, what points map to the vertices of that polygon. And if you don't know, and people really use this numerically, this is where it came up for me. Translating one domain to another to solve a PDE, one and then the other, or in computer graphics, also things having to do with large matrices. This became important. The spectral sets contained in polygon, whatever, it doesn't matter. The point is, we need to compute that map, and you can't compute it without these accessory parameters. And even these 19th century people knew it. And how do you find them? Well, there's all these numerical methods to find them, because it's really, if you use the wrong one, you get the wrong length. You'll get a polygon with the right angles, but the wrong lengths of the sides. That's bad. And you just adjust, there are ways of just adjusting and making it just a big thing, and using that Newton's method that we described earlier for tuning, the right parameters, just like you're training a neural network or something. But these guys see, they've answered like the prayer, like the greatest hopes of these 19th century.
Actually, I didn't know about this.
These 19th century mathematicians, where they said, like you can look at the equation itself, and you can use this thing, the isomonodromy of this. You can use the monodromy of what this function would have to be, or the actual things based on the function. This function is related to something that solves a differential equation, but this differential equation, you don't know the actual coefficient, but you know the monodromy, so you need to get the coefficient. So it's like this Riemann-Hilbert kind of problem. And the same function, this tau function, comes up.
Yeah.
And they use you need to evaluate, you need to find where does it have a zero in order to recover the coefficient. That's their idea. It's so wonderful. It's like, this is what I think all these guys were in the 19th century were aiming at and couldn't get. And now that there's all this conformal field theory and stuff about this, people actually know how to compute it, how to evaluate these zeros. And this is part of the story I don't really know. And I'm wondering if, okay, I'm just putting it out there because I'm curious about it. If you could at all connect, what the hell is this thing? Where does it come from?
All right, so I mean, tau functions. So, tau functions, there are different tau functions for different things. So that's the first problem, that's the first thing. And actually, there are different tau functions that arise in very different settings for the Ising model. I mean, for instance, Julien Dubellay, he came up with some tau functions that describe things related to the Ising model. And these are different from the tau functions that Palmer comes up with, or that my PhD student studied in his PhD thesis. Somehow, maybe there is a connection between them, but it's not obvious. And I've never been able to understand what is the connection. And for instance, someone who would know a lot of things about this, Igor Kritchever at Columbia, he told me, yeah, these things are related, but he did not explain to me in which way they are related. And like, since it's never not been written anywhere, it's a bit complicated to say to what extent they are related. So let me explain just the two settings in which this tau function arises. These two settings do contain the word isomonodromy, of course, because this is really, at the heart of what tau functions are. But so for the Ising model, the tau function miraculously somehow ends up being a scaling limit of correlations of Ising model spins. Mm-hmm. But how it arises as a tau function as related to the monodromies, it arises as, on the analytical side, you could say that there's a space of functions with monodromies around the spins. And the monodromies are fixed and very simple. They're just the square root type monodromies. So the function just changes sign once, making a loop around the point. So but the hard part is that the functions are not holomorphic. On the other hand, the tau functions, which are probably the ones that this Schwarz-Christoffel mapping business is about, and which are the ones that appears in Dubellay's work, they are multi-valued holomorphic functions with a monodromy that is a matrix.
Mm.
And so why these two frameworks would be equivalent in ways, I don't know. Obviously, you know, there are things that are similar, the fact that there's a monodromy, but you know, on the one hand, you have non-holomorphic functions with a fairly trivial monodromy, which is just the -1 monodromy. On the other hand, you have holomorphic functions, but vector valued with a matrix monodromy, which may also depend on the point, actually. But yeah. Okay, so, all right, so these are two instances of tau functions. So for Ising model, I mean, maybe the part I'm more competent to discuss. How do you see these functions that arise, you know, how do you see the spin correlations arising as tau functions of some analytical problem? Mm. And so the key idea is to perform kind of a fermionic excitation in your model. So you fix your spins and you inject a fermion somehow, and you see how that fermion moves. You get equations of motions for that fermion, and you get a PDE, which is not the Cauchy-Riemann equation, otherwise you would be holomorphic, but it's a deformation of it. So you get a PDE and you get monodromies as your fermion moves around your spins, you get some monodromies. And the reason you get this monodromies is actually fairly elementary. It's down to some combinatorial property. And okay, then here you go. You get some some functions that solve some PDE that has some monodromy with respect to the spins. And then why the tau function arises as the spin correlation is because you get some asymptotics of your solution. As the fermion goes close to a spin, you get, you know, some kind of interesting asymptotic that you can determine, and this allows you to say that the tau function of that problem, of that collection of solution to a PDE with some monodromy, is actually a spin correlation. And that allows you to compute spin correlations in a number of cases and relate them to Painleve equation. But yeah, I've never understood why these tau functions and those tau functions, they are related, and why they both give Painleve equation. I've never understood that, so sorry, I'm not able to answer your question.
I mean, I guess Painleve came at it from the other side, trying to classify, you know, just differential equations with
regular singular points and things like that.
That weren't movable or something.
Yeah, absolutely. But you know, the reason why the Painleve equation arises in the Ising model, somehow it's maybe the sign that our analysis was maybe not high level enough. We just see the equation that arises in the end of the day, right? You just get an equation, it happens to be the Painleve equation, and you don't know why. But so maybe, you know, some further analysis would be required to understand really why, you know.
Well, I thought
at this point we don't know.
I think there's some story that now it's far back that relates the Painleve equation to this isomonodromy, and you know, that the idea of the lax pair, and you need the compatibility equation of something, and then what are the I forget. This is the part of the story I really don't know well.
Yeah, well, I mean, so for instance, I don't know any lax pairs that arise for the Ising model. You know, that's a sign that things are either a little bit different intrinsically, or understanding at this moment of those things is different. But I've not seen lax pairs arising for the Ising model. Yeah.
Well, I hope that I have met this. In any case, that's one thing I'm curious about, and I feel like there's a challenge to say that the world is what part of the world is really, really complex, irreducible, cannot get away. Not just the complex numbers are just much more convenient and a much better, easier way of looking at whatever phenomenon it is, but but there, you really wouldn't have the phenomenon at all if not if for thinking about things in terms of
I agree. I may disagree on the part, is it really describing our world, or is it just describing the world that complex analysts like? But that is a maybe slightly different debate. But I wholeheartedly agree that either it's impossible or we are just not smart enough to see that it's not complex analysis, because it feels deeply complex analytic. No, I mean, there are things that are deeply complex analytic, like for instance, analytic number theory is deeply complex analytic. Whether it's part of a world or not, that's, I mean, for sure, aliens know about prime numbers, and probably they know about the zeta function, right? But I mean, aliens as being hypothetical intelligent civilizations that have developed an understanding of the world that allows them to travel in space. Okay, so that's what I define as aliens, right?
I would
so I cannot imagine you can travel through space and not know what a prime number is. But maybe maybe I'm wrong, but I think deeply that they know what prime numbers are. But yeah.
Okay, we've discussed a lot of math here, and I actually, I wanted to ask you about, some other things about your thoughts on academia, and of course, look, you brought up just now a very interesting question of like what math, if we really met an alien civilization, would they know the same math? A lot of people have thought about this question, and I wonder if. I don't know, maybe
we should ask more of this kind of questions, I think. Huh? We should ask more of this kind of questions.
We should ask more of these kinds of questions? Yeah. If we want, okay, then I would do that. If you wanted to have, let's do another conversation. We've already, I don't know, I've exhausted our, but we've covered a lot of good stuff, meaty stuff here in this first conversation. We can have another conversation for more speculative philosophical stuff. How about that?
Well, absolutely.
Terrific. Okay, I think because there's so much I can keep in my head. Thanks so much for.
My pleasure. Thanks for being such an entertaining and exciting host. And
this is I don't know if I'm that entertaining yet, but I hope I want people to learn something and find it fun and maybe the good conversation. Hopefully, we'll get there someday.
Yeah. Well, I mean, sure. I mean, you could have many more discussions about.
Great.
About AI, about aliens, about academia. Well, I mean, the latter one is a bit political, obviously. So, about many things about society.
You have thoughts on society too, huh?
Well, I mean, I can't help but think. That's the problem.
Huh?
Sometimes I wish I could stop thinking, right? But I cannot help thinking, and I guess always thinking in the in a way that's not written in the books for some reason. But that has served me well.
Only when you're trying to sleep if you're consumed with that, that's a problem. Okay, let's talk again. Let's talk. We have to make sure that we do it sometime, not in the too far future. Thank you so much.
Thanks.
Okay. Bye.